Today we're starting our final unit of the year. It's all about air, and we're going to kick it off by learning about the atmosphere, seasons, and global climate. In this Sun and Earth model, we are reminded that the Earth rotates on its axis once every 24 hours, and that is why we experience day and night. The Earth also makes one complete revolution around the Sun approximately every 365 days, and that is why we experience a year. But the key to this revolution is that the Earth is tilted at a fixed angle of 23.5 degrees, and that is why we experience seasons.
Hi, I'm Jared. Welcome to Fun Science Demos. The big idea today is actually a question. Why do we have seasons? Well, a lot of people think it's because the Earth is closer to the Sun. But through science, we've discovered that's really not the reason at all. The reason is pretty simple. The Earth is tilted. Put this pencil here to show you the axis. That's not really there in space, but the Earth's tilted. In one of our other science videos, we demonstrated that we have day and night because the Earth spins. Seasons, a different story, a different demonstration. Set the Earth over here. So let's take a look at the tilt. It takes the Earth one whole year to travel around the Sun. But look at the tilt. June, September, December, March down there, the tilt stays the same as the Earth travels around the Sun throughout the year. Now, let's get back to the demonstration and show you what happens to the sunlight and explain why we have seasons. So we've changed the room and we only have our Sun shining on our Earth. And right now, it's tilted away from the Sun. The top half of the Earth is tilted away from the Sun, and we have December. I also have this weird metal strap with holes in it. Now here's the important part. Each one of these holes are the same size, which means they let the same amount of light through each hole. Now we check this out. Let's watch what happens when we put the strap up. We can see the sunlight shining through the holes, but something's different on our Earth. So take a look at our dots. They're all different sizes as we go up the globe. Why? What's going on? Well, the same amount of light is getting through each hole, but the holes look different. Well, that means the light is more concentrated and the Earth underneath that is warmer. But as I go up, you can see the light is spread out. It's not as focused. It's not as concentrate up here because it's tilted away from the Sun. That means the Earth underneath that is cooler. We have seasons. Hi, I'm...
Now, a lot of people mistakenly believe that the reason for the seasons is because the Earth is closer to the Sun at certain times during the year. It turns out this is actually true, but it's not the reason for the seasons. The Earth is actually closer to the Sun in January, which ironically is our winter, but we are talking really large distances here. If you consider that the diameter of the Earth is about 8,000 miles, we are talking the difference between 91 million miles that the Earth is away from the Sun in January versus 94 million miles that the Earth is away from the Sun in July. These distances are so large that they don't have any impact on the temperature we are experiencing on planet Earth. The reason for the seasons is what that video just showed us. The Sun shines onto the Earth at different angles depending on the time of year and the location. So we live in the northern hemisphere, and when the northern hemisphere is tilted towards the Sun, it is summer. That's what you're looking at in the top part of this diagram. When the northern hemisphere is tilted away from the Sun, it is winter. And of course, it's the opposite in the southern hemisphere. The Sun shines equally on both hemispheres in spring and fall. The atmosphere is a layer of gases that surrounds planet Earth. And we have names for the different layers of the atmosphere, but we really need to only be concerned about the two layers that are closest to us. So the lowest layer is called the troposphere, and that is where weather happens. Right above the troposphere is the stratosphere, and that contains the ozone layer, which protects us from harmful ultraviolet radiation coming from the sun. What you see in this diagram is it's like a graph. The x-axis is temperature and the y-axis is distance from the surface of the Earth. So in the troposphere, the temperature decreases as we go higher and higher in the troposphere. But in the stratosphere, the temperature increases as we go higher and higher. And that's because the ozone layer is absorbing ultraviolet energy from the sun. There is a difference between weather, the day-to-day conditions in a certain area, and climate, the long-term average conditions in a certain area. It's important we understand the difference before we continue our discussion.
Never mind. Weather is not climate. Climate is not weather. The difference between these two terms is a matter of time. Weather is the condition of the atmosphere in the short term, from day to day. For instance, it snowed today. While climate is what we can expect from the atmosphere over a long period of time. It will snow at some point during the winter. More examples? Florida's a humid subtropical climate, and this is a hot, humid day in the Midwest. Phoenix is located in a desert climate. This is a dry heat in the plain. Never mind.
So there are several factors that influence Earth's climate. We've already started discussing unequal heating of the Earth by the sun because we've talked about the angle of the sun's rays and the amount of surface area the sun covers. But albedo also plays a role in the unequal heating of the Earth by the sun. A second factor are convection currents, and those are influenced by the Earth's rotation on its axis and a phenomenon called the Coriolis effect. And then all of these factors influence ocean current patterns. So we've already mentioned how there's variation in the angle at which the sun's rays hit the Earth. If you look at the equator, the sun's rays come straight on to the equator. They are perpendicular to the equator. But as you make your way from the equator to the mid-latitudes and then eventually to the poles, the sun's rays come in at an oblique angle. This is going to influence the amount of surface area at which the sun's rays are distributed. It's going to be more concentrated. The sun's energy is going to be more concentrated at the equator and less concentrated, or in other words, more spread out at the poles. We learned about albedo during the climate change unit. Albedo is reflectiveness. White surfaces are more reflective of solar energy, and black surfaces are less reflective. So if we consider the different topography on our planet, a place that has a lot of snow and ice is going to be light or white in color, and it's going to reflect a lot of the sun's energy back into the atmosphere. And we would say that places that have a lot of snow and ice, like the poles, have a high albedo, and therefore they're going to be cold. Contrast that with places like a tropical rainforest that have a lot of trees and green vegetation. They are going to be less reflective. We say they have a low albedo, and they're going to absorb most of the sun's energy and therefore experience hot temperatures. Our planet has an average albedo of about 30%, but again, at the extremes, like fresh snow, you're going to see high albedo versus a forest, which is dark in color, where you will have a low albedo. Now, this unequal heating is what drives air circulation on our planet. In other words, it creates the wind. So you can think of the atmosphere as a giant heat engine that is being driven by the sun. But before we can truly understand the wind patterns on planet Earth, we have to remember the basic properties of air. Now, the first one you already know about. You know that warm air is less dense than cold air, and therefore warm air rises and cold air sinks. Water vapor capacity means that warm air has a higher capacity, a better ability to hold water vapor as compared to cold air. This next property of air might be new to you. It's called adiabatic heating and cooling. It has to do with air pressure. As air rises, pressure on the air molecules decreases. This allows the air to expand, and this creates a general cooling on the surrounding air. And then the opposite is true. As air sinks, air pressure increases, causing the air to decrease in volume and create a general heating of the surrounding air. And then finally, we have latent heat release. If you remember how the water cycle works, you can understand this last air property. The sun will shine down on the surface of the earth and it will cause liquid water to evaporate. That means it's changing the liquid water into the gas form, which is called water vapor. And this water vapor will rise into the atmosphere. But eventually it will get high enough into the atmosphere where it will cool and then condense back into liquid water. So when water goes from gas to liquid, it releases energy and that warms the surrounding air. So that's called latent heat release. These air properties all play a role in convection currents on our planet. Convection currents can also be called convection cells. And on planet Earth, we have 3 sets of convection cells, both to the north and south of the equator. We have Hadley cells, Ferrel cells, and polar cells. We only need to learn specifics about Hadley cells and polar cells. Hadley cells is when air rises at the equator and sinks at 30 degrees north and south of the equator. Polar cells is when air rises at 60 degrees north and south of the equator and then sinks at the poles. And then right here near the equator is the Intertropical Convergence Zone, or ITCZ for short. It's the place on our planet that receives the most direct, intense sunlight because it's near the equator, and it's where the Hadley cells converge. And it explains why we have hot, wet climate all year round near the equator. This is an important diagram in your book, and you'll want to go through it several times over the course of a week or so your brain can process everything that's happening. But it's tying together all of those properties of air and showing you how they work together to create convection currents on our planet. So it all starts here at the Intertropical Convergence Zone, where the sun is coming in at a perpendicular angle to the equator and shining very intense heat energy. And it is causing that moist tropical air to rise. When that rising air gets high enough, it experiences adiabatic cooling, and that causes the water vapor that it is holding to condense and fall back to the earth in the form of rain. So that's why we have a lot of warm tropical rain near the equator. But look what's happening on top. The condensation of water vapor produces latent heat release. And this causes the air to expand and continue to rise farther up into the atmosphere. And as it does that, it's going to encounter some dry, cold air, and it's going to displace that. It's going to push it out to the north and south. And that dry, cool air, because it's more dense than warm air, is going to sink. And as it sinks, it's going to experience adiabatic heating. And it's going to reach the surface as warm, dry air and then flow back to the equator and complete this convection current. Convection currents are circular, but more importantly, it's going to be responsible for the hot, dry deserts on our planet. It is not a coincidence that the deserts are 30 degrees north and south of the equator. please take a 5-minute stretch break and we'll continue talking about wind.